Astronomers have discovered the next known black hole, Gaia BH1. It is a highly unusual binary system in which a sun-like star orbits a black hole with 10 times the mass of the Sun. The problem with this discovery is that the system does not fit into the known models of star and binary system evolution. Neither the common envelope model nor other theories can fully explain how the black hole could bind the star to itself without destroying it. This phenomenon once again challenges old principles of astrophysics, and the discovery suggests that there are still many undiscovered phenomena in the universe. A binary system is usually a system in which two massive celestial bodies, such as stars, planets, or black holes, are bound together by their mutual gravitation. The newly discovered system initially appears to be a normal binary system, but then facts emerge that have left scientists at a loss for an explanation. Black holes the size of BH1 are usually connected to their stars in very narrow orbits. However, the star orbiting this black hole is moving in such a wide and highly elliptical orbit that the duo seems simply impossible. No existing theory can explain the strange dance of the two. The Gaia BH1 system is about 1,500 light-years from Earth. The phenomenon was discovered by the Gaia mission, which has been measuring the positions, movements, and brightnesses of over 1 billion stars in the Milky Way since 2013. The aim of Gaia is to create a highly precise 3D map of the galaxy and thereby gain insights into the structure, origin, and development of the Milky Way. In addition to the general mapping of our galaxy, Gaia's search algorithms filter out any unusual phenomena from the data sets. The binary system caught their attention. The black hole is most likely a stellar mass black hole with 10 times the mass of the Sun. The companion star is a G-type main sequence star and is similar to our Sun, with a surface temperature of about 5,850 Kelvin. The star belongs to the lower middle of the most luminous stars in the universe. Scientists are now puzzling over the forces that have helped these two bind together. It's striking that there is no mass transfer between the star and the black hole. The star is not giving off any measurable mass to the black hole, and the black hole has only gravitationally bound the star to itself to the extent that it does not harm the star. Gaia made the spectacular discovery. It's almost unbelievable how many fantastic telescopes and observation satellites we are now using to unlock every little secret in the universe. In addition to NASA's James Webb Space Telescope, ESA's new Euclid Space Telescope is providing incredibly detailed images from the cosmos. The Gaia mission is also a project of the European Space Agency. The Gaia satellite is placed directly in space and scans our galaxy around the clock. As part of the mission, scientists are looking for regularities in the universe, but they're also looking for the unusual. From repeating structures, researchers can derive laws and thus understand the blueprint of the universe. The unusual thing about Gaia BH1 could be the portal to a new dimension of knowledge. At first, Gaia BH1 was recognized as a typical binary system, two massive objects bound by gravity. They share a common gravitational center and perform a cosmic dance that, at first glance, resembles that of many other binary systems. However, when the data was examined more closely, it became clear that this was no ordinary dance. After the companion star was identified, it was initially unclear who the dance partner was. When the black hole was discovered, the scientists' curiosity was also aroused. Binary systems of stars and black holes are a fascinating thing. After all, black holes normally devour matter, and thus also stars. If they bind to stars without harming them, as in this case, there is usually a balanced relationship of forces. The black hole binds the star only enough to allow it to orbit. However, the star is no longer attracted by the black hole's gravitational pull. This usually results in very specific structures, and our science thought it knew exactly the conditions under which such a dance is possible. But now, thanks to Gaia BH1, they are learning that they didn't know everything after all. The star orbits the black hole on an elliptical orbit with a high eccentricity of 0.45 and an orbital period of 185.6 days. This circumstance is actually not physically possible. The star should escape from the black hole when it's at the furthest point of its orbit, and the black hole should suck the star in when it approaches it again. But neither of these things happens. The star orbits the black hole over and over again in a safe orbit. So, what is it that binds the two together if it is not any of the known physical forces? At first, researchers suspected that one or even several other objects, such as neutron stars or white dwarfs, might provide stability between the two. However, all model calculations have so far yielded no meaningful results. A third or fourth partner would tend to destabilize the system. The dance of the two remains a mystery, and researchers sought answers. The next step was to check whether the second dance partner might not be a black hole after all. However, very specific oscillations in the orbit of the star clearly indicated the presence of a black hole. These oscillations, known as wobbles, are like an object's fingerprints. The wobble or wave of a neutron star looks very different from that of a black hole. Again, the questions could not be answered. Gaia BH1 attracted the attention of scientists for another exciting reason. The binary system was found in a very isolated location in space. Since no standard model of binary evolution can explain it, researchers speculate that there is an anomaly in this area of the universe. Gaia BH1 goes beyond common envelope evolution. Scientists love their theories, and when a system like Gaia BH1 comes along, the researchers of this world quickly find themselves in need of an explanation. When their cherished theories fail, heads start spinning and heated discussions ensue. Binary systems with close orbits are usually explained by common envelope evolution. The theory is abbreviated as CE. This approach is a model that attempts to explain how the dynamics in binary systems work. In the context of Gaia BH1, this model was used to understand how the black hole and the sun-like star could form their current system. However, there were some problems. The CE generally explains how a massive star, as the progenitor of the black hole, becomes a red giant and expands greatly. Then, a companion star enters the outer layers of the red giant. This common envelope surrounds both stars. Through friction and dynamic interactions, the system loses energy and the orbit of the two objects narrows. At the same time, the envelope is ejected. The final state is that the envelope is completely ejected. What remains is a close binary system. Most of the time, the star is a G-type star like in Gaia BH1, and the second object is a stellar black hole or sometimes a faint neutron star. This model does not fully apply to Gaia BH1 because the orbit of the sun-like star is much too wide to have been created by friction in a common envelope. The companion star has only about the mass of the sun, which makes it unlikely that it had enough energy to completely strip the large envelope of the progenitor star that later became a black hole. In the case of Gaia BH1, there is also no evidence that mass has been transferred from the companion star to the black hole, which is often the case in a close orbit. The explanatory approach fails completely here, and scientists are at a loss. No solution either: the triple star hypothesis. Let's take a look at the next system that has reached its limits with Gaia BH1. The triple star hypothesis is a model that assumes that Gaia BH1 originally emerged from a triple star system that became dynamically unstable and disintegrated, leaving behind the present system. The system thus began with 3 stars, 2 massive stars in a close orbit around the inner binary, and a lighter third star, probably the G-type star, orbiting the 2 in a wider orbit. The 2 massive stars in the inner system could have evolved faster than the outer star. They exploded as supernovae, leaving behind either a black hole binary or a single black hole formed by a merger. The formation of the compact objects inside made the orbit of the outer star unstable, resulting in the present-day configuration: a single black hole with the sun-like star in a wide orbit. The triple star hypothesis could explain why the companion star is so far away. The G-type star did not have to enter a common envelope, thus avoiding the laws of the common envelope evolution model. But overall, such triple systems are pure speculation since the preceding events cannot be reconstructed with certainty. They therefore remain pure speculation. So far, known triple star systems with massive stars and highly elliptical orbits are mostly unstable, which does not apply to Gaia BH1. Questions also remain unanswered with the triple star hypothesis, which is why it's not a sufficient explanation. Difficult to research black holes and binary systems. It's a fact that our science still knows very little about black holes and binary systems. Black holes play a significant role in astronomy, as they can tell us a lot about the evolution of massive stars, the dynamics of binary star systems, and even the origin of gravitational waves. However, they are not always easy to detect and are difficult to study, depending on the properties of the system and the activity of the black hole. Researchers use electromagnetic radiation as a source of information. Active black holes that draw in matter from their companion stars produce strong radiation, particularly in the X-ray range. This radiation is generated when matter spirals into an accretion disk around the black hole and is heated by extreme gravity. Such active binary systems with black holes are called X-ray binaries. Dormant black holes like the one in the Gaia BH1 system are so-called dormant or quiet black holes. They show no active accretion and can only be identified by their gravitational effect on the companion star. Precise astrometric data, such as that from the Gaia mission, can analyze the orbits and motion of the visible star. However, the possibilities quickly reach their limits when it comes to black holes. If the mass of the invisible partner exceeds the critical limit of about 3 solar masses, it's likely to be a black hole. Researchers also use gravitational waves, or the aforementioned wobbles, to identify black holes in binary systems. Gravitational waves are produced when two compact objects, such as black holes, merge. We currently have 2 observatories on Earth that are capable of measuring such waves: LIGO in the USA and Virgo in Italy. These observatories measure these waves with the help of the finest sensors. Wobbles, on the other hand, are generated by the visible movement of a star. The gravitational force of an invisible companion causes the star to wobble slightly, creating the typical wobbles.